So let's go back to our agenda. So introduction to powers. So before studying different types of motors, it is necessary to know and understand the basic principles about motors. Everything works on the principle that energy is conservative. To simplify things, let's dive into power. The input power equals output power. But in real world, there's a loss in power usually in the forms of heat. Because of these losses, not all the energy produced is converted to output. The measure of how much the energy is converted to the output is the efficiency. To be specific in motor, since we know that motor converts electrical power to mechanical power, let's replace the input power by electrical power and the output power by rotational power. So let's define mechanical power. In general, power is the rate at which work is done. So it's work over time. By definition, work is the dot product of force and the displacement. Since distance over time is velocity, therefore it will be equal to the force multiplied by the velocity. In rotational motion, force can be replaced by torque and the linear velocity can be replaced by the angular velocity. Electrical power is equal to the product of the voltage multiplied by the current. It's also equal to I squared R or V squared over R. Assuming that our system is 100% efficient, the electrical power equals to the rotational power. And by the equation that we have derived before in the previous slides, we can determine that vo- the voltage multiplied by the current is equal to the torque multiplied by the angular velocity. And what we can conclude by this from this equation? First, that the torque is inversely proportional to the angular velocity or angular speed. This conclusion proves that the concept that if the motor is a high speed, it has a low torque, and if it is a low speed, it has a high torque. Next is the torque is proportional to the current. This means that to control the torque, we need to control the current. If the motor has a low current, it is expected that the torque would also be low. And this torque is what we control in each and every motors that we use. We want to have a torque that is as much as possible constant. The motor rotates on the principle that there's a force that is acting on a current carrying conductor when there's a magnetic field which is present, which is defined by the left hand rule. This current carrying conductor is the moving part of the motor, which is called the rotor. It has a certain size and length. Therefore, we can use the Lorentz force equation to determine the amount of force. Again, the Lorentz force equation is equal to the charge multiplied by the vector product of the velocity and the external magnetic field. If we evaluate the vector product of the velocity and the external magnetic field, we will arrive at the equation would be equal to Q multiplied by the magnitude of the velocity multiplied by the magnitude of the external magnetic field multiplied by the sine of the theta, which is this one is perpendicular to both the velocity and the magnetic field. Since velocity is equal to distance over time, or it can also be length over time, this equation can be further simplified by replacing the velocity by length over time. We will have this equation. But since We know that current is equal to the charge multiplied by the unit time. We can replace this Q over T here by I. Then we will have this equation. So force is equal to BIL sine of theta, wherein this vector, this force vector, is perpendicular to both the velocity and the external magnetic field. If we multiply this force that we got, by the length of the rotor, we will get torque. And what we can conclude in this equation is that torque is proportional to the size of the motor itself. Therefore, if the size of the rotor is higher or bigger, that means it is a bigger motor and it has a bigger torque. And likewise, if the length of the rotor is small, therefore that motor is small, and then the torque will also be smaller. So let's discuss probably the most confusing theory about the motors. What is the difference between the power and the torque? Or the best question would be, is there really a difference between power and torque? Or is it an apple to apple comparison when you compare power and torque? In automobile point of view, some claims that this model is better than the others because it has a higher torque and vice versa. So which is better, higher torque or higher power? I have here an automobile, assuming that this is an electric vehicle from Tesla. This electric vehicle is traveling at a certain torque T and a rate of R. By using the principle and the equation that we have learned on the previous slides, the power that is used by this car is P. If the same automobile would be traveling at the same torque, but the rate would be half of the previous, which means it would be faster, the power that is used would be doubled. To define what torque and power, so let's define torque. The power is the rate at which work is done. In linear motion, work is the dot product of the force and the distance, which is equal to the mass multiplied by the acceleration and the distance. In rotational motion, force would be replaced by the torque and the distance would be replaced by theta. Similarly, the mass would be replaced by the moment of inertia, which is the quantity that opposes the rotational motion. The linear acceleration would also be replaced by the angular acceleration. So therefore, power is equal to the moment of inertia multiplied by the angular acceleration and the angular displacement divided by the time. Okay, so assuming that the rate t is equal to 1 second and the angular displacement theta is 1 radians. That means the power would be equal to the torque. That means the motor can rotate 1 radians in 1 seconds using torque T. And the power would be also equal to the torque T, since T and theta would be equal to 1. But if the motor would work faster, the power would also get higher. That means the torque provides the picture of how much the work is. while the power includes the element of time. So we have learned in the previous slides that torque is proportional to the angular velocity. If we would place the torque and the angular velocity in a Cartesian plane where torque is in the y-axis and the angular speed is in the x-axis, the graph would be similar to this, wherein the x-intercept would be the no-load angular speed, while the y-intercept would be the holding torque. In real motor, the no-load angular speed is low, is very, very low, but not zero. But for the sake of computation and calculation, let's assume that it would be equal to zero. By using Poincare law form, we should be able to determine the equation of this line. So, so this equation represents each and every points on this line. If we compute for the power, since power is equal to the product of torque multiplied by the angular velocity, we can multiply this torque equation by the angular velocity and this angular velocity by torque. And we would arrive by these equations. These equations are for power. These are equations of power. And these equations are parabola. The red parabola opens to the left side, while the green parabola opens downward. This equation tells us that if you want to maximize the power of the motor, you should be operating at half of its maximum speed or half of its maximum torque. And similarly, you can use the derivative, you can use its derivative to find the maxima. Is there any question before we can continue?